When you ask a smart speaker to set an alarm for 7 a.m., the response feels immediate. You speak, and the device answers. But that frictionless experience hides a massive communication gap. Humans communicate with messy analog waves, vibrations in the air that vary wildly in tone and volume. Computers, however, require rigid, structured digital data to execute a command. Natural human speech is full of stumbles, long pauses, and overlapping ambient noise from the room around you. Moving from that physical noise to a digital instruction is a process that requires more than a simple recording. The assistant doesn't use a single conscious brain to listen to you. It runs your voice through a pipeline, a lightning-fast relay race between specialized AI systems, each designed to solve one specific part of the translation. To see how this actually works, we have to freeze time at the exact millisecond your voice hits the microphone and track that data through 5 distinct stages of processing. Step 1 is audio preprocessing. Algorithms immediately identify and strip away ambient background noise, like the hum of a refrigerator or the sound of traffic outside, to isolate the core frequencies of your voice. In Step 2, feature extraction, the newly cleaned audio wave is chopped into tiny millisecond slices. By breaking the continuous wave into these discrete segments, the system can analyze the sound one piece at a time. This chart is a spectrogram, a visual map of sound frequencies over time. It allows the computer to see the audio as a data set rather than just hearing it as a signal. From this map, the system extracts critical acoustic features. It measures amplitude by the height of the data peaks and determines pitch by tracking the frequency lines. These extracted features are finally converted into phonemes. These are the smallest units of sound in a language, like the k, a, and t sounds that make up the word cat. This physical cleanup is the foundation of the process. It translates the chaos of the analog world into discrete, uniform nodes, preparing the signal for the first AI handoff. Those phonetic units now enter Step 3, speech to text. This is where an acoustic model begins the work of assigning actual alphabet letters to the phonemes it just analyzed. But the system doesn't rely on sound alone. A secondary language model acts as a contextual safety net, using statistical probability to predict which words logically follow one another in a sentence. This diagram shows the problem of homophones, words like weather and weather that sound identical. Because they share the same phonemes, the acoustic model cannot distinguish between them, leaving the probability meter stuck in the middle. The language model resolves this by looking at the surrounding context. When it sees the words determine the, it knows the probability of the next word being the meteorological weather is near 0, and it locks on to the correct spelling instantly. At this point in the pipeline, the machine has a perfectly transcribed digital sentence. However, it only possesses the text. It does not yet understand the intent behind the words. Step 4 is natural language understanding, or NLU. This is the cognitive phase of the pipeline, where the AI parses the plain text to find structural, actionable meaning. First, the system performs intent classification. It looks at the whole sentence to determine the goal, identifying that the phrase "set an alarm" corresponds to a specific internal command. Then it performs entity extraction, or slot filling. It pulls out the specific variables required to execute that intent, in this case, extracting 7 a.m. and converting it into a formatted time variable. This phase also handles the errors that often occur in natural speech. If a user stutters or mispronounces a word, the speech-to-text model might accidentally transcribe an illogical sentence, like "I need a break." Downstream NLU models use semantic context to recognize that these words don't make sense in this order. They can retroactively correct the transcription error on the fly, ensuring the system doesn't execute an incorrect action. NLU is the bridge between human unpredictability and machine logic. It ensures that a physical action is only triggered once the system has achieved absolute certainty about what you want. In Step 5, the structured data is fired to the backend API. This is the final handoff, where the software tells the hardware to actually trigger the alarm or pull the requested data. If you need a verbal reply, a text-to-speech system takes over. It uses deep learning to generate a human-like response, carefully calculating the rhythm and inflection to sound natural. Now we can unfreeze time. The smart speaker chimes and delivers the audible confirmation you were waiting for. From the outside, it looks like a single instant reaction. In reality, your voice just triggered millions of calculations and a series of complex handoffs between specialized AI systems. This choreographed microscopic relay race is what allows a voice assistant to conquer physical chaos in a fraction of a second.